This slide has a lot of detail to it, but it goes a long way towards explaining the trends that I just showed you. Why is it that something like toluene favors giving ortho and para isomers and not much meta? And indirectly also suggests why toluene reacts faster than plain old benzene does. All of these are the carbocation intermediates that are possible. Over on the left here you can see we have the three possible isomers that can form when you nitrate benzene. We've got our ortho, para, and meta. And within each of these there's three possible resonance forms that can be drawn. If you recall, when it comes to resonance, if you can draw more than one resonance representation for a molecule, that does make it more stable. So the fact that we can get that positive charge anywhere in that benzene ring is possible because of the stability that resonance brings. But it's also true that not all resonance forms are equal in stability. Some are more important for describing the molecule. When we look at the intermediate in this first row here for the ortho isomer, we can imagine that all three of these forms come together to make an overall structure that's hard to draw, but that would represent the single carbocation intermediate. And so notice that the nitro group is at the ortho position, the methyl group's at the top of the ring in every position. So all of these are representing the same product that we're trying to make. We're just looking at that key step of making that carbocation. And if you notice, the difference in these three have to do with the position of the double bonds in the ring, but what we're really focusing on is the position of that positive charge. And you can see this third resonance structure here is the one that is particularly stable. This is the reason why toluene is faster than benzene, because we can form a very stable tertiary carbocation if that positive charge is at the top of the ring, like you see there. Remember, tertiary carbocations are more stable than secondary, which is what's true of those other resonance forms to the left. And in fact, any alkyl group that's at the top of the ring is going to form significant amounts of ortho isomer, because when it does that, it can put that positive charge right next to that substituent, making, again, a particularly stable tertiary carbocation. Now in the middle row, if we are attempting to add that nitro group to the para position, you can see it's at the bottom of the ring in each case. There's also three possible resonance forms. We can again use those curvy arrows to show the electron pairs moving, but that also redistributes that positive charge. In each case, the positive charge is on a carbon that's only making 3 bonds, not 4 bonds. So none of these are going to be ultimately stable as a final product, but we have to form this along the way to getting there. And notice that it's the middle structure here for the para substitution. That's the one that gives us that very stable tertiary carbocation. And so we tend to get ortho and para in significant amounts. The percentages can vary as far as conditions of reaction temperature, and certainly if you have something other than methyl group, if it's ethyl or propyl or tertiary butyl, that can affect the product distribution between ortho and para, but we still tend to get only those two. Well, what's wrong with meta? If you look at the bottom row, what if we attempt to draw the structure where we're putting the nitro group at the meta position? Well, notice that all three of those produce secondary carbocations, but it's not possible to get the positive charge right next to that blue methyl group. That's why meta is not favored in reactions of toluene, because we don't get that particularly good stabilization that we can get with ortho and para. We do maybe get some meta, and remember, even the meta positions are more reactive than plain old benzene, but there's no particularly good carbocation intermediate in that meta row. They're just all so-so. And so as substitution happens, we tend to form products where we get particularly stable carbocations. They form faster, and so they're going to lead to the products that in this case correspond to ortho and para substitution. And for everything that directs ortho and para, it has to do with the stabilities of one of their carbocation intermediates.